minute or two, just to let people to continue to join, then we'll get started. Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar on basic drinking water math for operators. My name is Owen Volk from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it in the GoToWebinar dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information that you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have any questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through the request form, which I will be sharing shortly in the chat. One of the many ways EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application, falling short on project funding, not sure where to start? EFCN is here to help. Submit a request through the link in the chat to receive tailored support based on your project needs. And on that note, we can get started. I would like to introduce our presenter for today, Daryl Gotham, Senior Research Engineer at the Great Lakes Environmental Infrastructure Center. Welcome, Daryl. I will go ahead and hand it over to you.
Thank you, Owen. And thank you all for signing up and tuning in for this presentation. I hope that everybody gains some information from it. So we'll get started. So what are we going to cover in this course? We're going to cover calculating areas and volumes. We're going to look at some conversions. We'll cover flow rates. We'll have some stuff on pressure. We'll talk a little bit about pressure, and we'll spend some time working on the pounds formula and calculating some feed rates. So this slide just covers some of the different types of things that we're going to look at. We'll look into flow, pressure, volume, velocity. It also covers some of the different units of measurement that maybe we will need if we're doing basic drinking water math. You can see under flow, there's gallons per minute, million gallons per day, and cubic feet per second. So we'll work in a few different units of measurement for each of these different topics. So here we have just some of the different formulas for area. These tend to be helpful just to have available in case you come into these situations. Obviously, we're not going to come into the need for the area of a triangle all that often, but just useful to have. So with our areas, typically the ones that we look at the most in regards to water math are rectangular and circular areas. We'll find that rectangular areas it can be beneficial when we're looking at filtration and sedimentation calculations. So in this example, we have a rapid sand filter. It's got a width of 10 feet. It's got a length of 20 feet. And we look at our formula for the area as area is equal to length times width. We multiply our 20 by our 10 and we get 200 square feet. Moving on to the circular area. Once again, when we're looking at drinking water systems, quite often we'll have the need for to do this to do filtration and sedimentation calculations, and it also is important in our determining our flow rates for different sections of pipe. So in this example, we've got a circular sedimentation basin with a diameter of 60 feet, and we want to determine the surface area in square feet. So there's two different formulas. You know, the traditional one of area is equal to pi r squared, and then also something that's become a little more common more recently, area is equal to 0.785 times the diameter squared. So we can use either one of these equations, whichever one you prefer. As we can see, if we put in our 3.14 in place of pi, multiply that by the radius twice, radius times radius, we'll get 2,826 square feet. And if we place the diameter into the area equals 0.785 times the diameter squared equation, we calculate that out, we get the same answer. And we can do that because if we look here, this comparison of pi r squared to 0.785 times d squared, and we can see how they're equal. If we throw in d, we calculate the diameter here, or excuse me, the radius is d over 2. We place d over 2 in place of the radius, and we multiply that out. It actually comes out to the area is equal to 0.785 times d squared. So more commonly, we're going to use volumes in our calculations, and so these are you know, rectangular tank, cylindrical tank, and cylindrical pipe are the three most common. We've got a few others that are a little less common, but once again, we're throwing them in for reference in case somebody ever needed to calculate those volumes. They have the formulas they need. So in a rectangular tank, we're purely taking the area and then multiplying it, in this case, by the height. And then for the cylindrical tank, we're doing the same thing. We're taking the formula for the area, whichever one you use, and multiplying it by the height to get the volume. And then a cylindrical pipe is basically the same thing as a cylindrical tank. It's just on its side. We call that length instead of height, but it gives you the same idea. We're multiplying our area equation by the length to get our volume. So we're going to talk more about conversions, but as you can see from this slide, 1 cubic foot is equal to 7.48 gallons, and that's an important thing as we look through this. We'll use this as a conversion factor, 1 cubic foot equal to 7.48 gallons on several occasions throughout this, and it's an important one for our drinking water math. So we can do a calculation here. If we've got a 24 cubic foot tank, we can figure out how many gallons it'll hold. And we simply do that by taking our 24 cubic feet and we multiply that by our 7.48 gallons per cubic foot. And you'll see this throughout. I like to, in this case, I'm putting cubic feet in a different color because those will end up canceling out. And I'm a big proponent of using, writing out these equations and canceling stuff out so that you're certain that you've got the right units in your answer. So if we do this, we're going to cancel the cubic feet out. We multiply 24 by 7.48, and we end up with 179.5 gallons. All right, so on our rectangular volume, we'll do a rectangular volume problem here. So once again, our volume is equal to length times width times height. We've got a rectangular sedimentation basin. It's got a depth of 10 feet. It's got a length of 50 feet, and it's 20 feet wide. So we want to determine the volume first in cubic feet, and then we want to figure it out in gallons. So the first step is we're gonna determine the volume in cubic feet. So in this case, we take our length times our width times our height, 50 times 20 times 10. Note that we're gonna end up with cubic feet because we have 3 feet in here. We do that and we get 10,000 cubic feet. So to determine our volume in gallons, we've got to use our conversion factor of 7.48 gallons per cubic feet. Our cubic feet are going to cancel out. We'll be left with an answer in gallons. If we multiply that out, we end up with 74,800 gallons in that 10 by 20 by 50 tank. All right, so let's work a cylindrical volume example. So in this case, we've got a cylindrical tank. It's got a radius of 10 feet. It's got a height of 20 feet, and we want to know how many gallons it will hold. So if we remember, the first thing we need to do is we need to determine the number of cubic feet we have, and then do our conversion to gallons. So here's our formula. You can use either one of these once again, but we determine our volume in cubic feet by multiplying 0.785 times the diameter times the height. In this case, in my example, I'm using the volume is equal to pi times the radius squared times the height. So we put in our 10 feet for our radius, we square that, we multiply by 20, and we multiply by 3.14, and we get an answer of 6,283 cubic feet. But we want it in gallons, so we need to take and do our conversion from cubic feet to gallons. So if we take our 6,283 cubic feet, we multiply by 7.48 gallons per cubic foot, our cubic feet cancel, and we end up with an answer of around 47,000 gallons in that tank. All right, so we are on to our first poll. The poll is a new 800-foot section of 8-inch diameter water main was recently installed. The water main needs to be filled for testing. How many gallons of water will be required to fill the water main? Do we have that poll up, Owen?
Yep, poll's running.
All right, thank you. And if you could give, 3 minutes or so for people, that would be great.
Yep, no worries. Okay, we're gonna give it another minute. Okay, another 15 seconds. Okay, so results for the poll. 23% said 300,636 gallons. 16% said 2,351 gallons. 47% said 2,109 gallons. And 13% said 10,569 gallons.
All right. Thank you, Owen. All right, so let's go through and work this problem and see what the answer should be. So our 800-foot section of 8-inch water main, we want to, it's filled for test. We need to fill it for testing, and we want to know how many gallons it's gonna take to fill that. So if we take our formula for our volume and we multiply that by the conversion factor, so we're going to take this rate from the information we have right into the number of gallons. We need to take into consideration that it's an 8-inch pipe. So because of that, we're going to do a conversion where we're going to convert from inches to feet. So if we convert our 8-inch pipe into feet, it's 0.67 feet. We put those numbers in, so we've got 0.785 times 0.67 times 0.67 times the length of 800 feet, and then multiplied by our conversion factor of 7.48 gallons per cubic feet. Our cubic feet will cancel out and we'll be left with an answer in gallons. If we do that, we get 2,109 gallons. So answer C. I think probably one of the bigger things with this was the conversion of that from 8 inches to a foot. So speaking of conversions, this table, I put it in here I think it's a helpful thing. I'm not sure how many people are just interested in learning about water math, or how many people are looking to take operator certification exams, but these are definitely, as I studied for my operator certification exams, these are definitely factors that I took into consideration, things I wanted to learn, to memorize. So I suggest, if you're in that situation, maybe you want to have these at your disposal. But if you're given something in cubic feet and you want gallons, you multiply by 7.4. If you're given something in gallons of water and you want it in pounds, you can multiply by 8.34. And then these bottom two we would utilize in situations where we're working with pressures. So definitely some good conversion factors to be aware of. So let's look now at an example of doing a conversion. So in our example, we're given, we have 16,456 gallons of water that we need to transfer to a basin. All right, we need to know what is the minimum number of cubic feet that the basin must be in order to adequately hold this much water. And then from that, we also are curious as to, all right, what's the weight going to be of that water in pounds? So the first thing that we're going to do is we want to convert from gallons to cubic feet. So far, all we've done is gone from cubic feet to gallons. So now we're going to go in the other direction. So we need to make sure that we're using our conversion factor the correct way. So this question, do we use 7.48 gallons per cubic foot or 1 cubic foot per 7.48 gallons? And we have to use the 1.1 cubic foot per 7.48 gallons in order to get our gallons to cancel and to have our answer in cubic feet. So if we do that, we divide the 16,456 by 7.48, we get 2,200 cubic feet. Now, or the next part of this is we want to convert from cubic feet to pounds. We could have converted from gallons directly to pounds, but we went through the process of determining the number of cubic feet, so we might as well use that to determine our pounds. So we're going to take the number of cubic feet and we're going to multiply that by that conversion factor that goes from pounds, or that gives us pounds and gets rid of our cubic feet, and that's 62.4 pounds per cubic feet. As we see the cubic feet cancel, we're left with an answer in pounds, and that's 137,280 pounds. And these, we will commonly go through and you flip these conversion factors so that they give us, they get rid of what we want to get rid of and they give us what we want. So it's, if we use those, we write them out, quite often we can figure out an answer just based on what we start with and what we want to come up with. So we'll talk a little bit now about rate of flow. So rate of flow is an indication of how much water is moving past a spot in a unit of time. So it's volume over time. So our flow rates are typically referred to as discharge, and we express those discharge in volumes per units of time. So we look at these three at the bottom: gallons per minute, so the gallons the volume, the minutes the time, million gallons per day, volume per time, and cubic feet per second is the same. So so there's an important concept. We have a bunch of different units that we could potentially use here. So flow rate is in essence gallon per time, or volume per time, in this case gallons per minute. So we've got an example where we have a pump that fills a 5,000 gallon tank, and it takes that tank 12 minutes to fill it. So what is our output? What's the output of this pump based on these conditions? So we determine what our flow rate is. We take our 5,000 gallons, we divide it by the 12 minutes that it takes to fill it, and that gives us 416.7 gallons per minute. That's how quickly that pump will fill the tank, or that's the flow at which that pump operates to fill the tank, I'm sorry. So next step, if we use this pump, the same pump, and we run it for a full day, how much water would it pump? So here's more information that we can gain just by understanding how to utilize the math and the conversions. So in this case, we've got 416.7 gallons per minute. Now we want to get it in gallons per day, so we're going to multiply by 60 minutes an hour per hour, right? So that's going to get rid of our minutes. It'll give us something intermediate of gallons per hour, and then we know that there's 24 hours in a day. So we multiply by 24 hours per day. Our hours cancel, our minutes cancel. 416.7 times 24, that gives us 600,048 gallons in one day. So that's how much that pump will pump in a day. So if you wanted to, another conversion that you could potentially memorize would be the number of minutes in a day, and we can do that separately. We take our 24 hours in a day, we multiply by 60 minutes in an hour. We'll get a response or an answer that's the number of minutes in a day of 1,440 minutes in a day. And if you're welcome to memorize that if you like. I myself like to go through the different steps here. You could add it in and determine the number of seconds in a day as well. All right, so flow is equal to the area times the velocity. So this is another important concept. We'll cover this here. Units typically for flow, we're going to see are cubic feet per second. For our calculations, more or less, we want to get things into these units. The area will be in square feet, and our velocity will be in feet per second. All right, so we have flow is equal to area times velocity. So we've got water moving in a 6-inch pipe, and it's at a velocity of 2 feet per second. So what is the flow in cubic feet per second? So we need to first determine, we got to convert our pipe size from inches to feet. So we're working in the same units. We just divide our 6 inches by 12 inches per foot, and that gives us a half a foot. So we know what our diameter of our pipe is, so we're going to calculate the area. So if we calculate the area is equal to 0.785 times 0.5 times 0.5. We run that calculation, we're going to get 0.19625 square feet. So we've got our area. We know that flow is equal to area times velocity. They gave us our velocity already, so now we need to use that the formula for flow. Q equals our area of 0.19625 square feet times our velocity of 2 feet per second. We're going to end up with cubic feet per second because of we've got feet squared and feet per second, and our answer is 0.3925 cubic feet per second. All right, so we can look at conversions between CFS and GPM. So quite often we're given something in CFS and we want to go to GPM, and really what we're doing is we put in here the number of cubic feet per second that we have, we multiply by our 60 seconds per minute, and we multiply that by the 7.48 gallons per cubic feet. Cubic feet cancel, seconds cancel, and we get something in gallons per minute. So to go the other direction, we're given a given number of gallons per minute. We're going to multiply by 1 minute per 60 seconds. We'll multiply that then by 1 cubic feet per 7.48 gallons, and that'll give us our CFS. Minutes cancel, gallons cancel. We're just left in cubic feet per second. So we'll do an example of each of these. The first one, we have a pipe that has a flow of 0.5 cubic feet per second. What's the flow in gallons per minute? So we simply put that into our formula, 0.5 cubic feet per second times 60 seconds per minute times 7.48 gallons per cubic feet. Our units cancel out so that we end up with gallons per minute, and that's 224.4 gallons per minute. So now we'll work a problem where we go from gallons per minute to cubic feet per second. We have a pipe that has a flow of 500 gallons per minute. What is the flow in cubic feet per second? So we take our 500 gallons per minute, multiply by 1 minute per 60 seconds, multiply by 1 cubic foot per 7.48 gallons. I'm using this equation right here. Gallons cancel, minutes cancel, and we get 1.11 cubic feet per second. Okay, so that's how we do conversions for our flow. Now the next thing is there will likely be opportunities where you're given the flow and you're given the area, but you need to determine what the velocity is. So we're going to manipulate our equation, our Q equals A times V, to get velocity on one side. And we do that by dividing both sides of the equation by A. So if we divide both sides by A, we get Q over A on one side, we get A times V over A on the other side, and the areas cancel out on the right-hand side because A over A is equal to 1. That leaves us with the velocity is equal to the flow divided by the area. All right, so let's look at an example problem where we determine the velocity. So we've got a pipe with a cross-sectional area of 0.23 square feet. So they've spared us from having to calculate that out, but And that pipe has a flow of 0.75 cubic feet per second. So what is the velocity? All right, so we put the flow in the top of our formula, 0.75 cubic feet per second. We put the area in the bottom, 0.23 square feet. Two of the cubic feet on the top will cancel out with the square on the bottom, leaving with feet per second, and that answer is 3.26 feet per second. All right, so now we're going to add another twist. We're going to do our flow velocity, and we're going to require that there's a conversion involved. So we've got a pipe that has a diameter of 18 inches, and it's got a flow of 800 gallons per minute. What is the velocity of the flow in the pipe? So in this example, first thing we need to do is we need to get our units the same. So we've got 18 inches, doesn't really work very well with our formula, so we're going to convert the inches into feet. And if we divide our 18 inches by 12 inches, that gives us 1.5 feet, 1.5 feet. Next, we determine our area using the 0.785 times the D times the D. We put the diameter is 1.5 feet. We calculate that out. We end up with an area of 1.766 square feet. So the next thing is to put that into to determine what our flow is. So we were given a flow of 800 gallons per minute. We need to get that into cubic feet, so our units are the same. So 800 gallons per minute times the 1 minute per 60 seconds times 1 cubic feet per 7.48 gallons. Gallons and minutes cancel. We end up with cubic feet per second. We crunch the numbers out and we get 1.783 cubic feet per second. So now we have our flow and we have our area. And so we need to use our velocity is equal to the flow divided by area. So our last step is to put in our answers here. We've our flow on the top and our area on the bottom. And we do that, we're going to be left with 1.01 feet per second. So that's our velocity of flow in that pipe. Okay, so now we're on to poll question number 2. So what flow in GPM is needed to flush a 500-foot section of 6-inch water main at a velocity of 5 feet per second? So Owen, if you can bring that up and let me know you've got it up, and then we will give them about 3 minutes to work on this one as well.
We got it running.
Thank you.
We're about halfway there, everyone. Okay, 30 more seconds. Okay, so for the results of the poll, 8% said 733.9 GPM, 65% said 440.4, 15% said 98.1, and then 13% said 23.4.
All right. Thank you, Owen. So let's look at the solution to poll number 2. What flow in GPM is needed to flush a 500-foot section of 6-inch water main at a velocity of 5 feet per second? So we've got our 6-inch water main, 500 feet. First step, we want to determine what the pipe area is, and we have to remember that this is a 6-inch pipe, and we need to use our formula. We want to have it in feet, so we have to make this conversion to half a foot. So if we do that calculation, we end up with 0.19625 square feet. So that's the pipe area. Now, next we're going to look at our flow is equal to the area times the velocity. We know that we were given a velocity of 5 feet per second. So we take our area, we multiply that by the 5 feet per second, and that gives us a flow of 0.98125 cubic feet per second. And we want that our answer to be in gallons per minute. So now we have to do a conversion. So in our conversion, we're taking our cubic feet per second, we're multiplying by 60 seconds in a minute to get that into the minutes part of the GPM. We multiply by 7.48 gallons per cubic feet to get rid of our cubic feet and get our answer in gallons. And if we do so, we end up with 440.4 gallons per minute, or answer B. All right, thank you all. Let's move on. So now we're going to talk briefly about pressure. All right, so the idea behind pressure is that water exerts force over a unit of area. So, water has weight, it exerts force. Pressure is typically expressed in pounds per square inch or pounds per square foot. We know that water weighs 8.34 pounds per gallon, and we've talked today about there being 7.48 gallons in a cubic feet, in a cubic foot, excuse me. If we were to go through and multiply those two together, we can find out that water weighs 62.4 pounds per cubic feet. So these are kind of the three main conversions that we have for water gallons, cubic feet. So those are the important ones. So if we want to look at conversion of PSI, we know that a square foot is equal to 12 inches times 12 inches. So a square foot is going to be equal to 144 square inches. So if we take 62.4 pounds, if we're looking at 1 foot of water, we take 62.4 pounds per square foot. We multiply that by 1 square foot per 144 square inches. We do those calculations, we're going to have an answer that is in pounds per square inch. And so for every foot of water that we have in height, we've got 0.433 pounds per square inch. So if 1 foot of water height is equal to 0.433 pounds per square inch, if we take our 1 PSI and we flip this over and we divide 1 by 0.433, that means that 1 PSI is equal to 2.31 feet. So these are the other, from my conversions that I had mentioned, these are the other two, so that there's 1 foot is equal to 0.433 psi, and 1 psi is equal to 2.31 feet. Typically, that's another situation. If you can remember one, you can work your way around by flipping your conversion factors around. So let's look at an example. So in this example, we've got a ground storage tank. The ground storage tank is 10 feet wide by 20 feet long, and it's 6 foot deep. So we've got 6 foot of water in there. So if we were to do that calculation and we'd convert from cubic feet to gallons, we'd find out that we have 8,967 gallons of water when it's full to 6 foot. So we can also figure out that there's 74,850 pounds of water there. So that's the 8.34 pounds per gallon times the number of gallons. And so all of that weight works on just the bottom. So it's putting the pressure just on the bottom of the tank, the 10 by 20 foot bottom. So what is the pressure in PSI on the bottom of the tank? So we can calculate that out. So we know that there's 6 foot of height. We know that that each cubic foot weighs is 62.4 pounds. So we figure out that there's 370 pounds per square foot. That's the pressure. But we wanted to know what it was in PSI. So we're going to have to do the conversion into PSI. So we have established that 1 square foot is equal to 144 square inches. So if we take our 375 pounds per square foot, we multiply that by 1 square foot per 144 square inches. So our square feet are going to cancel. We're going to be left with units of pounds per square inch, which is PSI. That's what we need. And it works out to 2.6 pounds per square inch, or 2.6 PSI. So this slide, sometimes it's helpful for people to look at pressure as cubes of water stacked on top of each other. Sometimes that's helpful. And if we take and we look at that and we say that each one of those cubes that's stacked on each other weighs 62.4 pounds, and it exerts pressure on a 1 square foot area. So once again, if we've got a height of 6 feet, we're going to be 6 of those 62.4 pounds, and they're going to be stacking up on each other, and it equals out to a total of 375 pounds per square foot. So as we said, 1 square foot is equal to 12 inches times 12 inches, or 144 square inches, and our 375 pounds per square foot, if we convert that into PSI, it's 2.6 PSI for every 6 feet of water. So that relationship, we talk about waterhead, we're converting the pressure of our 62.4 pound cube of water from the pressure on 1 square foot to the pressure on 1 square inch is simply taking our 62.4 pounds, multiplying that number of square inches in 1 square foot. And so that's how we get that there's 0.433 PSI in 1 foot of water. I showed this, I guess, previously. 0.433 PSI is equal to 1 foot head of water. Divide 1 by 0.433, that gives us 1 PSI is equal to 2.31. Here's another example. It can be a difficult concept, so I apologize if I may be overstating it, but each PSI is equal to 2.31 feet. And it adds every 2.31 foot of water is another PSI. So if we've got a standpipe, and the standpipe is filled to 40 feet, there's 40 feet of water there. What's the pressure at the bottom of the standpipe? So we take the number of feet we have, and we're going to multiply by that by 1 PSI per 2.31 feet. So our feet are going to cancel out here, and we're going to be left with 17.3 PSI. So in a 40-foot high standpipe, we're going to have 17.3 psi. So now let's quickly look at an elevated storage tank example where we've got pressure. In this case, we've got a 100-foot high elevated storage tank, and it sits on top of a 30-foot high hill. The water in the tank is 11 feet from the top, okay? It's 11 foot below the top of the tank, and there's a hydrant at the base of this, at the bottom of this hill, okay? And what is the pressure at the hydrant nozzle? The hydrant nozzle is 2 feet up from the ground, assuming that there's no water movement, no flow, no head loss in here. So to do this, we're going to calculate the feet of head. So we're going to take our 100 feet here. Now we have to subtract off 11 feet because the top of that tank, it's not full all the way to the top. So we're going to subtract that off. We're going to add in the 35 feet because it's down the hill, but we need to subtract off the 2 feet for the nozzle. So that's going to basically tell us that from this mark down to the 2-foot nozzle, what the number of feet of head that is. So that's 122. So now if we want to know what's the pressure in PSI, we can take our 122 feet and we can multiply by either of these factors. So I put it in here so you can see. Like I said, if you can remember one, you can work these problems. You don't have to know both. But if we take our 122 feet, we multiply by 0.433 psi per foot, and that'll give us 52.8 psi. And if we multiply our 122 feet by 1 psi per 2.31 feet, we get the same answer. And so the next, we're going to look at concentrations. Simply parts per million that's 1 part per 1 million parts of something else. And quite often what we're talking about is a part per 1 million parts of water. Milligram per liter is the same thing. They're equal. And technically, when we look at milligrams per liter, we're talking about the number of milligrams weight per a 1 liter sample of water. So it's weight per volume, but because a liter of water weighs 1 million milligrams, it basically amounts to the number of milligrams per million. And so that's the same as parts per million. Percent, most of us should have this down. It's really the equivalent of parts per 100 parts. So it's more similar to parts per million than one would have thought. 1 per 100 is expressed as 1%. In the case of, if we're looking at this, 1% is 10,000 milligrams per liter, and that's equal to 1%. And just to note that, if we're to that equivalency, if we're going back and forth between decimals and fractions, 1 over 100 is expressed as 0.01. So the last main concept that we're going to cover is calculating feed rates. We need to note that dry chemical feeds, we're usually looking at things in pounds per day. If we're talking about liquid chemical feed, we're talking about things typically in gallons per day. And then the other important concept is that we need to do some conversions if our chemical strength is not 100%. So here's another formula that's important to remember and understand, is that our flow in million gallons per day is times the dosage in milligrams per liter or parts per million times the weight of water per gallon will give us the number of pounds per day of a chemical that we're dosing. And for liquid chemicals, specifically things like chlorine, we need to take into account that it's not 100% available and that we need to divide by the weight of the chemical in each gallon. So our pounds formula, our feed rate is equal to our flow times our concentration times 8.34 pounds per gallon. So we'll look at this example. We've got a well that produces a flow of 600 gallons a minute, and the chlorine dose is 1.5 parts per million. What is the feed rate for gas chlorine in pounds per day? So we know our flow is in gallons per minute. We're going to have to convert that into gallons per day. We've got our dosage in parts per million or milligrams per liter. So the first thing is convert flow to million gallons a day. So we take our 600 gallons per minute. Here's that factor that does a direct conversion to minutes per day. So we multiply that out. On the top, we're going to end up with gallons per day. On the bottom, we've got 1 million gallons divided by mg, or million gallons. And so that's basically dividing it by 1 million gallons divided by a million gallons. What it does is it brings our mg up here and makes it a little easier to understand. So we do that, our gallons cancel, our minutes cancel, and we end up with something in million gallons a day. In this case, the answer is 0.864 million gallons a day. So now we've got our flow. Now we've got our concentration. They gave us that, and so we put that into our pounds formula. 0.864 million gallons a day times 1.5 parts per million times 8.34 pounds per gallon, and that gives us an answer of 10.8 pounds per day. So as I had said, for liquids, it's a little different, and this is probably one of the more common dosage calculations that we're gonna be involved with when it comes to water, and that's the number of gallons a day for the for feeding sodium hypochlorite, which is liquid chlorine. So our gallons per day is equal to the million gallons times the parts per million times 8.34 pounds per gallon. But we also have to take in some other factors. So the top is basically the same as our pounds formula, and it calculates, pure pounds. The bottom is where we take into consideration the strength of the chemical, and also the weight per gallon, because chemicals are not the same as water. They don't have the same weight. So it ends up being this is what our formula ends up being: gallons per day equals million gallons a day times parts per million times 8.34 pounds per gallon, divided by the percent strength times the specific gravity, which we'll cover here briefly, and then 8.34 pounds per gallon. So that specific gravity times 8.34 pounds per gallon tells us what the weight is per gallon of our chemical. So specific gravity, it is the ratio of weight of a substance to the weight of water. Okay, that's what specific gravity is. And we know that water weighs 8.34 pounds per gallon, and it has a specific gravity of 1.0. So water is the standard. So it's at 1. So if we had a chemical that had a specific gravity that was greater than 1, that means it's heavier than water. And if it's lighter than 1, then it's lighter than water. So as we'll see, chlorine has a specific gravity of 1.2 in this example. It's 12.5% sodium hypochlorite, and so it's heavier than water, which means that the pounds per gallon is going to be higher for that. So what we do to determine how many pounds per gallon there is in a chemical is we take that specific gravity, we multiply it by the weight of water, and that'll give us the pounds per gallon. So let's look at an example for liquid chlorine feed rate calculations. What is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2 when the plant flow is 0.5 mgd and the dosage is 0.9 parts per million? All right, so we know our gallons per day gallons per day calculation is flow times concentration times 8.34 divided by the percent strength times the specific gravity times 8.34 pounds per gallon. We know that, we've been told that, right? So we just throw, in this case, we're just going to throw our numbers in. So 0.5 million gallons a day times the concentration, the dosage we had was 0.9. Our percent strength, we're going to convert 12.5% into a decimal, so that's 0.125. Specific gravity is 1.2, and we know the weight of water is 8.34. If we calculate that out, we're going to get 3 gallons per day. All right, and then we can once again, we've done this before today, we can rearrange our formula to get something different. So in this case, if we want to determine what the dosage is, we can take our our million gallons a day flow and our 8.34 pounds per gallon. And we can divide both sides of this equation. So we're going to take them and we're going to put it on that side of the equation. We're going to put it on this side of the equation. And when we do that, our flow is going to cancel and our 8.34 pounds per gallon is going to cancel on the right-hand side of the equation. And we're going to be just left with our dose is equal to our pounds per day divided by this flow times 8.34 pounds per gallon. So if we can rearrange this equation to solve for dose. So there will be times where we're given the pounds per day and we're given the flow and we want to know what the dose is. So we're gonna work a problem like that. We've got an operator that checks the settings at a treatment plant and notes that the gas chlorine feed rate is set at 30 pounds per day and that the plant flow is 2.1 million gallons a day. What is the dosing parts per million being administered? So our dose is equal to our pounds per day divided by our flow times 8.34. And in this case, we've got 30 pounds per day feed, 2.1 million gallons a day. We calculate that out to 1.71 parts per million. And because it's gas chlorine, the concentration is 100% and we don't have to worry about that. So we've got our final poll. A groundwater well produces a flow of 350 gallons a minute. The chlorine dose is 1.3 parts per million. What is the feed rate of gas chlorine in pounds per day? All right, Owen, thank you.
Like the other ones, we'll give it about 3 minutes.
Yeah, that'll take us pretty much to the end, but yeah, that sounds great.
Awesome. Okay, we're about halfway there, everyone. Okay, 30 more seconds. Okay, so results of the poll. 10% said 3.52 pounds per day. 15% said 4.65 pounds per day. 70% said 5.46 pounds per day. And 6% said 6.82 pounds per day.
Great, thank you, Owen. I will quickly try to go through the solution to this so that everybody can get back to whatever they're going to do after this. So our groundwater well producing flow of 350 gallons per minute. We've got a chlorine dose of 1.3. What is the feed rate in pounds per day of gas chlorine? So the first thing is to convert the flow into million gallons a day. We do that by multiplying our 350 gallons per minute times our minutes to day conversion, and then we divide by 1,000,000 gallons per million gallons, which is that gives us a 0.504 million gallons a day. And so the next thing we want to do is we want to calculate the flow in pounds per day. So we take our 0.504 million gallons a day, multiply it by our concentration, by the weight of water per gallon, and we get 5.46 pounds per day. So the answer is C. So what do we cover? We talked about volumes and areas, conversions, flow rates, pressure, the pounds formula, and feed rates. Some of the more important takeaways that areas and volumes can be necessary for determining a variety of different things, including flows and concentrations. Conversions are important, useful in manipulating the information that we're given to get the information we need. And then both rates for both feed and flow are critical ideas for proper operation of drinking water systems. I want to thank everybody for participating. Feel free to share your thoughts in the chat. Is there anything that was new to you that you learned? Anything that made you think? Is there anything that I can clarify or make easier to understand? Feel free to ask your questions.
So yeah, we did have one question come in right towards the end. For that final poll question that we had, they were wondering, so with the answer being 5.46, you had mentioned about percent strength and specific gravity. They were curious, when do you use that and when do you ignore that?
Okay, that's a good question. So in this case, we're talking about gas chlorine. And so you take that into consideration when specific gravity is for liquid chemicals. So gas chlorine is different. We're talking about it in pounds per day, and we would talk about the liquid chemicals in gallons per day typically. So because it's gas chlorine and it's 100% available, we don't have to worry about the concentration or the percent available concentration. We don't have to worry about the specific gravity. None of that comes into play into this because it's different. Given more time, I would have loved to have gone through a solid to show how it works to calculate for a solid, because that's even slightly different. So if you're using a solid chlorine.
Okay, awesome. We do have another question coming in. Do constituents and added chemicals in the drinking water change the flow rates at all?
So if we're adding stuff to the flow rates, typically not, because they're dissolved. Any changes that might, you could, in theory, if you're adding something, it could make the water denser. There's always those possibilities, but usually we're talking about things that are in such small concentrations that it has little to no effect on that.
Okay, awesome. And I think that answers everything.
Okay.
So a huge thank you to Daryl today for sharing his expertise with us. Following today's webinar, you'll receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following the webinar so you can let us know your thoughts on today's session, as it helps us plan for future webinars on topics that are important to you. Thank you again, and we hope to see you at future EFCN events.
Thank you, Owen.